In this video, we're going to look at the concept of complex numbers and eventually get to the point where we can talk about how we can represent these using sort of a polar form, similar to the polar equations that we looked at in the last couple of videos. So what we're used to typically dealing with are real numbers. So these are the types of numbers that we think of all the time. So real numbers. These are numbers like the number 1 or the number -3 or the number pi or e. So all of these are examples of real numbers. They can have decimals, 2.74395, ... These are the types of numbers that we've dealt with. We've got whole numbers, so numbers like the 1 and the -3, these are integers. We've got pi and e, these are real numbers that are sort of what we think of as sort of transcendental numbers. They have no repeating decimals, they go on forever. And we have some that can terminate, rational numbers. All of those things are the same. So we think of these as the numbers that we're used to dealing with, and we denote them with a symbol that looks like this when we're dealing with real numbers. So this is the set of real numbers. We've also probably seen what's called imaginary numbers. These come up whenever you try to take the square root of a negative number. So for example, if you try to take the square root of -1, we're going to call that number I. And these show up often where you've seen them when we try to solve quadratics. So recall the quadratic formula. May have been a while since you've seen this. But the quadratic formula looks like this. If we're trying to solve ax squared plus bx plus c equals 0, this has solutions that look like the following. X is equal to -b plus or minus the square root of b squared minus 4ac whole thing over 2a. Well, it's this piece right here with the square root that yields what can possibly become imaginary numbers. So if b squared minus 4ac is negative, less than 0, then we get basically imaginary numbers from that term. So this is the idea. An imaginary number is just anything where we're trying to take the square root of a negative number. The result of the quadratic formula is actually what we call a complex number. Complex numbers have both a real, so they have both real and imaginary parts. So for example, on the quadratic formula, this term, this -b over 2a part, that's a real number. If both a and b are real numbers, this will just be the ratio of those two pieces. And so that'll be a real number. But this part can potentially be an imaginary number. and we'll have this combination that has part real number, part imaginary number. That's what we call a complex number. So these will take the form, generally speaking, of the following. Often we'll use the letter Z when we're talking about a complex number, and we'll write it as A plus B times I. Let me just give myself a little more space. It's a little wonky here. Let's write that a little nicer. So A plus B times I. Just note that A and the B that I'm using here are different from the A and B over here. This was an unrelated example. But the idea is this part is going to be a real part, and this part, because that I right there is the square root of -1, that whole piece is what we call the imaginary part. So it has these two different components. These numbers, again, they show up solving quadratics. They show up in a number of things you'll be introduced to down the line in solutions of differential equations, in complex analysis, justifying certain things you may see in a linear algebra course. So this is all stuff, basically all stuff that are tools that you may encounter and need to use down the line. So that's kind of why we're focusing on that here. Okay, so this is the form of our complex number. There we go. And we can plot them in what we call the complex plane. So we can graph these. The complex plane looks like our normal Cartesian plane, but instead of labeling the axes x and y, we're going to label them real. So this will be our real axis, and I may just use the letters RE for that. And this one up here is going to be our imaginary axis. And again, we may just use the letters IM to abbreviate that down the line. And if this is the point that I'm interested in, this is maybe our A plus BI, what it means is we went a distance of A, so that distance right there is A, in the real direction, and a distance of B in the imaginary direction. Let me erase this part right there. So that's kind of the idea of how you would plot one of these points in the complex plane. Whatever the real part of the number is, you go that far along the real axis, which we associate with the x-axis. Whatever the b is that's sitting with the I, that's the imaginary part, we go that far in the imaginary axis, which we associate with the y-axis. These things follow all the same types of rules that we're accustomed to with real numbers. So, for example, addition and subtraction. So, if I want to add a couple of numbers, so this is, it works how we'd expect. So if I can delete this here, works how we'd expect. So, for example, if I wanted to add two numbers together, here's my first complex number. I'll call it z with a subscript of 1. So z1 is 1 plus I, and z2, our second complex number, is maybe 2 minus 3i. Then z1 plus z2 is going to be equal to 1 plus I plus 2 minus 3I. And you add them piece by piece. So I would add the real numbers together. The 1 from this one and the 2 from this one, they add together and give me a 3. So 1 plus 2. And the imaginary parts, we have a 1I here, and I'm adding a negative 3I. So 1 minus 3 is going to be minus 2I. That's how we would add those together. It will also work similarly if we start to plot these things. If we plot them, so if we plot these points as well, what we'll see is the following. So here is my graph with my real and imaginary axes. Let me draw some hash marks on here just to give us a sense of where these points are. So there's 1, 2, and 3 in the real direction, 1, 2, 3 in the imaginary direction, negative 1, negative 2, negative 3, and so on. So for example, the point Z1, 1 plus I go 1 in the real direction, and I also go, you imagine that there's a coefficient sitting in right there of a 1. 1I, so I'm going to go positive 1 in the imaginary direction. There's going to be a point right here. So there's the point Z1, which is 1 plus I. For the second point, Z2, we would do that similarly. I go 2 in the real direction and then negative 3 in the imaginary direction. So here's 2 in the real direction and then 3 down in the imaginary direction. That would put me at the point right about here-ish. So 2 over 3 down. There is the Z2, which is equal to 2 minus 3I. And if we add them, this had a plus 1 in the real direction, this had 2 in the real direction, so I'll wind up going 3 in the real direction. This was 1 in the imaginary direction, this was negative 3 in the imaginary direction. That 1 minus the 3 will lead a negative 2. We'll wind up at this point right over here. Here is the Z1 plus Z2. We just add the real distances together, add the imaginary distances together, and that's what it winds up looking like. As another example, you may see, I don't want to focus on it a ton, but we may see inequalities involving these complex numbers. So I may ask you to plot an entire region, and we're going to use what's called set notation. So let me go over this real quickly. Let me write it down and we'll go over what it means. So I'm going to plot this set called S, and it's going to be equal to the set, we use a little curly bracket there, of A plus BI. Then you'll see a vertical line. Sometimes this is, instead of a vertical line, they'll use a colon here. But that A is greater than 1, B is less than or equal to 2. So what does this mean? This is set notation. So this whole piece right here is set notation. And it means the following. It basically says the following sentence. S is the set of basically all numbers of the form A plus BI where, or such that, let me be more precise. Typically they'll use the word such that A is greater than 1 and B is less than or equal to 2. So this is the sentence of how you would read this notation. S is, so S equals, the equals corresponds to the word is, so we can kind of color code it here. S, the equal sign goes with the word is. When you see these symbols, those curly brackets, that's how we know we're talking about a set. Let's see if I've got other colors here. Let's see. Do an orange one. So here's all numbers of the form a plus bi. Let's see what other colors. Purple, such that that's what this symbol right here means. And then hopefully the last couple are obvious. That goes with that. And in fact, I think those are obvious enough. I can just underline that whole thing. So color by color, this is kind of how they go together. S is equal sign. The set, whenever you see curly brackets, we're talking about a set of all numbers that take this particular form, all numbers of that particular form. Vertical line right here means such that these conditions are met. So we'll list some set of conditions. So that's the idea. We are wanting to plot the set of all these, basically the set of all these complex numbers where the real part of the number, the a, is greater than 1, and the imaginary part of the number, the b, is less than or equal to 2. And so we can do that in the following way. We draw our axes. Let me label them. Here's our real axis. Here's our imaginary axis. And I'm interested, again, in all the numbers where the real part is greater than 1. So if I say that this is 1, 2, and so on, 3, and the imaginary part is less than 2, so 1, 2, and so on. I'm interested in all the points to the right so that their real part, their x coordinate, is greater than this line. And because it's a strictly greater than symbol, I don't want to use the points that are actually on the line, so I'll use a dashed line to indicate the cutoff where we transition from a less than or equal to 1 to a greater than 1. For the b values, that's the imaginary part, so I'm going to go along the y-axis, the imaginary axis, and I'm interested in the values of b that are less than or equal to 2. Because it's a less than or equal and I am including 2, I will indicate that with a solid line instead of a dashed line. And so I'm interested in basically all of the points in this shaded region. This is the region that we care about. Just try not to cover up what I've already drawn too much. But this is the idea. We've split things up. I'm interested in values of a to the right of 1, a is greater than 1, and b's, the y values, less than or equal to 2. So including the 2 and everything less. So it has to be to the right of this dashed line and below the solid line. That is the shaded region that I've indicated there. So you may see some inequalities like that pop up. I just wanted to give you some indication of how these things may be written. The next thing I want to talk about is what's called the modulus, or essentially the magnitude of a complex number. It's the modulus, or magnitude of a complex number. If we're dealing with a complex number z, the notation that we'll use is going to look basically like absolute value symbols. So let me just make this totally clear. This is how we're going to denote it. So the modulus of a complex number z is given by one of the following. Is denoted, let me write that, it's denoted one of the following ways. Either with what appear to be absolute value symbols, or in some texts they'll use what appear to be double absolute value symbols, like double vertical lines. Both of these are used pretty interchangeably, depending on the textbook, so expect to see both of them at some point in the future, even though our textbook, I believe, just uses this first notation. So, one way to think about it is, so what it means is the following. If I talk about the modulus of z, I'm talking about the modulus of this a plus bi number, and it's the magnitude, it's the distance of that number. If we look at this example of all these points that we plotted, how far is this number from our origin? So basically, I want to think about the modulus as that distance from there to there, this straight line distance from the origin to the point. So with that in mind, we just get basically right triangles. It's the distance formula, which is basically just the Pythagorean theorem. It's just the square root of the x component squared plus the y component squared. So it's just the square root of a squared plus b squared. In a sense, in talking about the polar forms, this is the same as what we called r in the polar forms, where we just used x and y in place of the a and the b. But that's essentially what we're doing here. A is just representing how far we're going in the x direction, b represents how far we're going in the y direction, or in this case in the real direction for a, in the imaginary direction for b. So essentially this modulus term, it plays the same role that r played in our polar coordinates. So if I wanted to, for example, ask you to plot using the same set notation, so T is going to be the set of all z such that the modulus of z is less than 2. What does that wind up looking like? Well, I'll draw my axes. Draw that a little better. There we go. Give myself some room. So there's my real axis. Here's my imaginary axis. Go a distance 2. Distance 2. I'm asking for every point, so every number z in this plane, such that the distance, the modulus of z, so the distance to the point is less than 2. So the distance from the origin to that point is less than 2. That's going to give me a circle. And because it's less than, I will again use a dashed line to indicate the boundaries. But basically, we're getting a circle with a radius of 2. That is the region that we're dealing with. So let me draw my circle a little nice, and I'll come back and fudge where I put this hash mark there so it actually looks semicircular. Okay, so there is basically the border of this thing, and we're interested in the entire interior region of this shaded circle. So that's the set of all points in our complex plane where the modulus of the point is less than 2. The distance from the origin is less than 2. This modulus is going to play an important role. Generally speaking, it's sort of more important than the a plus bi form. We're interested in knowing the modulus, and we can use it in writing our numbers in a polar form. And this is going to be, in a lot of ways, a more common way to deal with complex numbers is in their what we call their polar form. So it plays an important role in this field, in the field of dealing with complex numbers. So it's often convenient to express these numbers in their polar form. Polar form. Which is going to utilize this modulus piece. So let me focus on that here, the polar form of complex numbers. Oh, I meant to mention this earlier. So just as a little side note here, let me sneak it in over here. This is the symbol we use if we're talking about real numbers. We've seen earlier this semester, this is the symbol we use. Sorry, not this one. Yes, that is the one that I mean to use. This was the symbol that we used to represent the set of all possible integers. We did that when we were looking at all the possible solutions to trigonometric equations where the solutions are periodic, and we used this symbol when we talked about how you could add basically 2 pi times any integer to get another solution. Complex numbers use this same kind of notation, but as a sort of a double layered version of C. So this is going to be a shorthand notation, so I don't have to keep writing out, I guess I should use bigger parentheses there. So I don't have to keep writing out the word complex numbers. I may just start to use that symbol. So just know that that little script C, that's going to be the symbol that we use for complex numbers. Okay, so a complex number Z, which is equal to A plus BI, also has a polar form. And that polar form is going to look like the following. So the polar form looks like this. Z equals R, where R is the modulus, times cosine of theta plus I sine of theta. So this is how it all relates to trigonometry. This is why we're introducing it in a trig class and not some other algebra class. So this is the form where, just to be totally clear, R is the modulus of Z. So it's just the square root of the a squared plus b squared terms. And theta is defined in a similar way that we did when we did polar equations. Tangent of theta was equal to y over x. In this case, that's b over a. So essentially it is the angle to the point that we're looking at from the sort of the real axis. So we'll do an example in just a minute. So again, r is the modulus of z, and theta is an argument that we can use that represents essentially an angle. We're going to be able to manipulate these numbers a little bit more easily. We added no problem before, but now we're going to be able to multiply a lot more easily. And so we'll see that in just a minute. So let me show you just a quick example of how this is used. If I give you the following, so z is equal to, I don't know, 1 minus I, and I want you to write it in polar form. The way that we would do this is we would first need to figure out what r is, and it's the modulus of z, which is going to be the square root of the a number, which is a 1, so 1 squared. That term right there is coming from this number, plus a -1 squared. And that -1 comes from the coefficient of the I term. There's a -1 sitting in front of that I. And so if I add these together, I get the square root of 1 plus 1. This is square root of 2 is the modulus for this one. We can use the argument tangent of theta is equal to our b over our a, so -1 over 1, and find theta. But in reality, the easiest way to do it is to actually just draw the picture of where this thing shows up. So let's draw the graph of this number. We can figure out the angle that way. So here's our real axis, here's our imaginary axis, and the number z, which is 1 minus I, means we go 1 in the real direction and then -1 in the imaginary direction. So I'm going to go 1 in this direction, I'm going to go -1 in this direction, and it's the point sitting right here. And so that distance right there is our modulus, so that distance is our square root of 2. This is our value of r. And this angle right here is the theta that we need. And it looks like in this case, based on this picture, theta is going to be equal to -pi/4. That's a -45-degree angle. If you wanted to go the other direction, you could go around that way instead and write it as 7pi/4. It's not going to matter. So this is just a polar representation. Let me clean that up just so it's less messy so we can see it a little more easily. There we go. Okay. So basically, with this in mind, the polar form is the following. Z is going to be equal to r, which was the square root of 2, times the cosine of -pi/4 plus I times the sine of -pi/4. And you can always check by actually evaluating what these values are, right? The cosine of -pi/4 is going to be √2/2. This will also be negative √2/2, so positive √2/2, negative √2/2. Distribute this √2 through, and you will wind up getting back the number that we were looking for previously. You'll wind up getting back the original form, which was 1 minus I. So I'm not going to do that right now. This is the polar form. So this is what the final answer looks like for this problem. However, there's a much nicer way to write this. So this isn't in your textbook. So I want to talk about this nicer approach though. So again, as you do the homework, this is the type of solution they'll be looking for. I want to give you the solution that I think is a much nicer form and a lot easier. So a nicer approach involves using something called Euler's formula. And there's a lot of things called Euler's formula. Euler was a very prolific Swiss mathematician, did a ton of stuff. In fact, the number e that we use in exponentials, like if you're looking at e to the x, that e is sometimes called Euler's constant. That's why it uses the letter e. It stands for Euler. So there's a lot of stuff named after him. He has a formula. I'm going to give you this formula. I cannot justify this formula to you. Justifying this formula requires a bit of complex analysis and would require essentially an additional math class to explain. But it basically gives a relationship between sine and cosine and e, that number that I was just talking about. So here's what it looks like. It says e to the I theta. If you take e and you raise it to a power that is imaginary. So this I represents the same I that we've been talking about, the square root of -1. E to the I theta is cosine of theta plus I sine of theta. This is Euler's formula, and it's a really, really useful and important formula. Going back up to where we define the polar form of our complex numbers, here it is, z equals r times cosine theta plus I sine theta. And what I'm telling you is right now, this cosine theta plus I sine theta, I can replace that whole thing in parentheses with just this e to the I theta. And the thing that's going to be really nice about that is we will be able to use all of the rules of exponents that we're accustomed to. So when it comes to multiplying two things, I'm not going to have to FOIL out a bunch of stuff with cosines plus I sines and figure out which parts are real and which parts are imaginary. I'm going to be able to just multiply exponentials, and when you multiply exponentials, you add the exponents. We'll be able to use those same rules. So instead of writing z equals r times cosine theta plus I sine of theta, as our textbook wants, I'll start writing them this way. We'll write the alternative, z equals r e to the I theta. And this is going to be a much easier way to manipulate these polar numbers. So again, I can't justify this formula to you without a whole additional course, but it's going to be something you'll see again. I used it in my calculus class. It's a really nice formula to use. And it actually relates a bunch of really cool things. I'll just do a little quick side tangent, so let me just sneak this in here as well. So this is not super important, but it's a nice little side note. If we so let me write a complete sentence here. If we let theta be equal to pi, we get a really interesting formula. So we will get e to the I pi equals cosine of pi plus I times the sine of pi. And thinking about what these numbers mean, based on our unit circle, so e to the I pi on this side, what is the cosine of pi? Well, that is, real quickly, that's over here, that's where pi is. Cosine is our x-coordinate on our unit circle. So cosine of pi is -1, and then the sine of pi is the y-coordinate of this same point, which is 0. And we wind up with e to the I pi equals -1, or if I add that -1 to the other side, we get this kind of cool formula that says e to the I pi plus 1 equals 0. This is just kind of a cool statement. This whole piece here is a side note, so we don't really need it all. Just sneak this off here. But a lot of times people refer to this as one of the most beautiful equations in all of mathematics. And the reason for that is that it relates basically like the 5 most fundamental quantities in all of math. It incorporates the number 0, which hasn't always been around. It wasn't in early number systems. Most of them left out the number 0. It includes the number 1, unity, the building block for all of our integers. It includes this number pi, which typically shows up in the context of things related to circles. And it's just this profound universal constant that shows up. It includes E, another profound universal constant that doesn't seem like it's related at all to pi. And then it also includes I, the building block of our imaginary number system. So it includes these 5 profoundly different quantities into one single equation. It's really, really cool equation to see that somehow our universe tied these things all together. It winds up bringing up questions again of, is this something that is discovered? Is this something that is invented? Does it exist outside of humans? You can get into all kind of math philosophy questions when you start to see these profoundly beautiful relationships between seemingly unrelated quantities. So that's it for my side tangent on that. Long story short, I'm going to vastly prefer, coming back up here, I'm going to vastly prefer using this form of our polar form of our complex numbers, as opposed to the version above it that involves the cosine and sine terms. So technically this is the part that tied it to trig, and now I'm saying let's abandon the trigonometry and just deal with exponentials, but it's really intuitive now because we'll manipulate these complex numbers in the same way that we manipulate exponentials, and you don't have to follow any of the weird rules in the book about how you manipulate these sines and cosines together. So, now that I've got that out of the way, so just coming back to our example, so coming back to z equals 1 minus I, we said in polar form, the original polar form, this was the square root of 2 times the cosine of negative pi over 4 plus I times the sine of negative pi over 4. So this is just the example we did a minute ago. I'm not doing any new math here. This is just the example we did a minute ago. And I'm saying now, the way I'll prefer to write this is as z equals square root of 2, there's the value of r, times e to the I theta, which is pi over 4, and I'll put the negative sign out in front of the I. So there's the polar form of this in both the version with sines and cosines and now in the exponential form. And again, this is the form that I prefer to use. Makes life a lot easier. So for example, we can now multiply numbers So we can multiply complex numbers easily using basically just exponent rules. Exponent rules. Okay, we can multiply complex numbers in their non-polar form, the a plus bi forms, and you just have to FOIL everything out. But now we don't have to FOIL stuff out. If we've written them this way, it's just exponent rules. So let's do an example. Again, I'm going to give you two numbers. Here's my first complex number. It's going to be root 2 minus root 2i. And my second complex number, I'll say, is going to be 1 plus I. And I want to know, so I want us to find z1 times z2. I want to find their product. So if I just put them in polar form, real quickly, I'm going to draw over here so we can get the angles. So here's the real axis, here's the imaginary axis. One of the points is 1 plus I, so this is our z2, 1, 1. So this is the point z2. z1 was at root 2, negative root 2. Root 2 is about 1.7, so maybe here-ish. And then we have to go down also that same distance. So if there's negative 1 and negative 2, here's negative 1.7-ish. Here's z1. So one of them and the other one. There's sort of the directions that we have to go. I'm looking for these two angles, our theta 1, so to speak, and our theta 2, if my pen will work. There we go. Those are the two angles. So looking at this picture, Z1, I just need to figure out what R is. What is this total distance along from here out to this point? And I can do that by taking the square root of the sum of the squares. So this distance we will do, so notice for this one, R is going to be equal to the square root of root 2 squared plus negative root 2 squared. When I square that root 2, it'll be just 2. Same thing with this one, it'll be 2. I'll have 2 plus 2, I will get 4. This is just the square root of 2 plus 2, which is the square root of 4, which is 2. That distance right there is supposed to be a distance of 2. So we've got 2, and it's e to the I times the angle. What is this angle? That is a 45-degree down angle, so this is e to the negative I pi over 4, because it's an angle of negative pi over 4. For the second point, which is the one up here, the one that I drew first, here's Z2, that is a positive 45-degree angle, and I'm going 1 over and 1 up. That distance, the R value for this one, will be the square root of 1 squared plus 1 squared, which is just going to be root 2. So the second one is going to be root 2 e to the I times positive pi over 4. And if we multiply them now that we have them in this polar form, Z1, Z2, that product, has some funky formula again in the book for how you do this, but for us with the exponentials, this is just 2e to the negative I pi over 4 times root 2 e to the positive I pi over 4. And our rules for exponents say that if you're multiplying two numbers together like this, first, these coefficients out front, I can pull them all the way out front. So I'm going to rewrite this as just 2 root 2, group those numbers together, e to the negative I pi over 4 times e to the positive I pi over 4. So I'm just copying basically just move this root 2 from where it shows up out here. How do you multiply exponents? When you multiply exponents, or exponentials rather, with the same base, all you need to do is add the exponents. So in this case, I will have my 2 root 2 out front, and I'll have e to the power of negative I pi over 4 plus positive I pi over 4. And what happens when I add those two together? That's 2 root 2 times e to the, well, they just cancel each other out. One's positive, one's negative. They're the same value. That's e to the 0. And what is e to the 0? That whole piece is just 1. So this is just 2 root 2. The result of multiplying these two complex numbers is just 2 root 2. And it turns out we would get that same value if we just FOILed these out. I guess I can do that really quickly as well. So if we FOIL in non-polar form, this is not going to be something you need to do a ton, but just what we would get is that Z1, Z2 was, let's see, one of them was root 2 minus root 2i, and I'm multiplying that by 1 plus I. I believe those are the two numbers. Let me just check. Yes. Root 2 minus root 2i and 1 plus I. And we would just FOIL them out. So this times this, then this times this, then this times this, then this times this. So the first would be the root 2 times the 1. We'd get root 2. Then I'd get plus root 2 times I. Then I'd get minus root 2i times the 1, so just minus root 2i. And then lastly, I would get minus root 2. I have an I, and I'm multiplying by another I. So let's simplify what we've got here. First, those cancel. They're the same thing with opposite signs. In the second piece, I've got root 2 minus this other number over here, which is root 2 times I squared. And I want to think about what that I squared represents. So remember that I is equal to the square root of -1. Square root of -1. So I squared means I'm taking the square root of -1 and I'm squaring it. And when you square a square root, they undo each other and we wind up with just -1. So that's what I squared is equal to. Whoa. Move that back so we can see a little better. There we go. So this I squared is just -1. And we wind up with root 2 minus that -1 times this other root 2 is a negative root 2. Minus a negative means we add, and we wind up getting 2 of these root 2's. So root 2 plus another root 2 is 2 total root 2's. And we get the same result in both cases. Generally speaking, though, again, this will be the preferred way. Okay. Let's do one or two other quick little things related to this concept, and we'll call this video a wrap. So in addition to multiplying these complex numbers, we're also going to be able to now raise them to powers, and that includes both integer powers and fractional powers. So we can be able to find, the square or cube or so on of a complex number, but we can also find the square root or cube root and so on of one of these complex numbers. And all of this requires us to look at something called de Moivre's theorem. So de Moivre's theorem says basically the following. If z, our complex number, can be written, I'm going to do the version of de Moivre's theorem that's the exponential form. In the book, they do the version with the sines and cosines, but again, this is much, much easier with the exponential form. So if it says, if z is equal to r e to the I theta, then what is z raised to the power n? Well, that's just going to be r e to the I theta raised to the power n. But what happens when you raise something like that to the power n? Well, you separately raise r to the n and then the e to the I theta. Whenever you have a exponential that's raised to a power and then that in turn is raised to a power, you multiply. So if you are multiplying two exponentials with the same base, you add the powers. If you are exponentiating an exponential, you multiply the exponents. And so we get e to the I n theta. So this is what de Moivre's theorem says, and it doesn't matter whether n is an integer or if n is a fraction like a half and we're finding a square root instead. So essentially what this is saying, we can use this to find, so we can find roots. So find powers and roots of complex numbers. powers are pretty straightforward. The roots are a little bit trickier because, as we've seen, when you take like the square root of a number, square root of 4, I'll delete this in a minute, square root of 4, there's two different numbers. Sure, that's 2, but it's also negative 2. Either of these numbers, when I multiply it by itself, will give me the 4. So when we take a square root, it is typically a multiply valued function. So we want to maintain that. That same thing is going to be true when we're dealing with these complex versions. So let's say we want to find the nth root of a function. So if z is equal to, again, re to the I theta, and n is some number greater than 0 that's an integer, then z has n distinct nth roots. And they're given by the following. So the notation that is often used is this little thing that looks like a W. It's actually usually the Greek letter omega. I should draw it more round like that, but W's close enough. So WK equals, we would do r to the 1 over n, and then we would do e to the I theta plus 2 pi k over n, where now k is equal to 0, 1, 2, and so on, all the way up to however many nth roots we're taking, 1 less than that, so up to n minus 1. So this is our formula. Let's put it to use in an example, and then we can call it a day here. So let's do this one last example. Let's say I want to find the cube roots of z equals, let's say, root 3 plus 1i. So, first thing to do is put it in polar form. So I need this in polar form. Just let me draw the little sketch over here to the side. Here's what this graph is going to look like. We're going the real direction. We're going root 3, which again is about 1.7. So if this is 1 and this is 2, maybe we're going to right about here-ish. And then we're going 1 in the imaginary direction. So we're basically going to this point right here. So I want that distance and that angle. There's my r and my theta. This r is going to be basically the square root, so r is going to be equal to the square root of root 3 squared plus 1 squared. And root 3 squared is going to be 3. 1 squared is 1, so this is the square root of 3 plus 1, which is the square root of 4, which is 2. And what is that angle? Well, I recognize it as one where I go, again, we're going root 3 in this direction and 1 in this direction, so that distance is 1. That longer distance is root 3. I don't recognize that angle with those numbers, but if I did them both as dividing by 2, then I recognize, oh, this is a number from the unit circle, or an angle on the unit circle rather, and this is the pi over 6 angle. So let me delete those, but that is pi over 6 right there. So in polar form, our z is going to be 2e to the I pi over 6. And so now we can find, in this case, our 3 roots. So has 3 cube roots. So we will see what this looks like. let's find what we'll call W0, the first root of these roots. So what we'll do is we'll do, again, 2 to the 1/3 power, right, because we're finding a cube root. And then we have e to the I, so go back to our formula, just make sure I've got them both on the screen at once so you know what I'm doing. Okay, so here's our r to the 1 over n. Our r was 2, n is 3, so we got 2 to the 1/3, and now we're doing this part. E to the I, r theta was pi over 6. I'm adding 2 pi times k, but our particular k is this number down here. It's 0. So 2 pi times 0, and then I'm dividing that whole thing by 3. And so if I simplify this, that 2 to the 1/3, I can just write that as the cube root of 2. And this 0 over here will make this entire term 0, so I really just have pi over 6 divided by 3, which is going to be pi over 18. So e to the I, pi over 18. So there's one of the roots. The next root, W1, so again, I'm just letting k go through these values. We just did the k equals 0 case, so k equals 0. Now I'm doing the one where k is equal to 1. So I'm going to plug in a 1 into this same formula. I get the same 2 to the 1/3 in front. All that's going to change is this angle, so it's going to be e to the I. We've still got our pi over 6, but now I'm doing 2 pi times 1, and then dividing that whole thing by 3. And so I still get the cube root of 2, but now the number I get here is 2 pi plus an additional pi over 6 that I'm then going to divide by 3. So let me get a common denominator just for the top. So the pi over 6 plus 2 pi, this 2 pi I can think of as being 12 pi over 6. Right? That would be the same as 2 pi. 12 pi on top, 6 on the bottom. That simplifies to 2 pi. So I've got 1 pi over 6 plus 12 pi over 6. That's 13 pi over 6 that I'm then dividing by 3. So I'm going to get e to the I 13 pi over 18. And the last root, e to the, is going to be the same idea, but now I'm doing 2 pi times 2 in that formula and dividing by 3. And I'm going to get, again, the cube root of 2, e to the I. So now I'm doing 4 pi plus an additional pi over 6. So this is now, you can think of it as 25 pi. So 24 pi over 6 would be 4 pi. This is 4 pi. Plus an additional pi over 6 would be 25 pi over 6 that I'm then dividing by 3 to get 25 pi over 18. And those are the 3 roots. One kind of cool thing about this is if we draw where these roots occur. Here's my real and imaginary axis. If we do this, I can draw them all on the following shape. Okay, so there's my poorly drawn circle with a radius of the cube root of 2, not the square root of 3. The cube root of 2 is that distance. Our first one occurred on this circle at an angle of basically pi over 18. So that's a third of the normal pi over 6 angle. That's way down here. Here is where that first pi over 18 angle occurs. The next angle is at 13 pi over 18. This direction, 180 degrees, would be the same as pi, so 18 pi over 18. If I'm only going 13 pi over 18, that's going to be somewhere up in basically this vicinity. So that angle right there is the 13 pi over 18. And then the last one, 25 pi over 18, we've definitely gone more than pi, so here's 18 pi over 18. And as we go through it, we'd have 19 pi, 20, 21, 22, 23, 24, 25 would be somewhere right around down here. And what you'll notice, hopefully, so there's 25 pi over 18, is that these three roots turn out to be completely evenly distributed around the circle. So they're evenly spread out. They occur at all of these nice even intervals on our circle. So we'll do some more examples before the final exam in the review of this stuff. There's plenty more in the book, but for now, that's going to be our entire video.